All right. Aloha mai kākou o Kelly Mariko anoia kupu'uwai Lewis ko inoa no wai ehu ma ka mokopuni o Maui he kanaka noi I Pekema ma NASA JPL. Aloha everyone. My name is Kelly Lewis. I'm born and raised in Waiahu, Maui. And I'm, as of this week, was appointed to a scientist position at NASA JPL. I intentionally introduced myself in my language because I think my island and where I grew up was probably my greatest teacher in how non-point source pollution impacts people on a day-to-day. I live maybe about 10 minutes from a river, and whenever it would rain, it's cloudy, and as kids, we want to go swimming in the river like right after. We're like, oh, we didn't get a chance to go play outside. But my mom, or just our parents in general, would be like, all the wild boars that run in the mountain, that rain, what is it going to do to our river? It's going to bring in potentially their waste in the river and bacteria. There's a ton of cesspools in Hawaii that says 83,000 cesspools. It's the most of any state. The cesspools in people's yard. If there's an overflow with the big rain event, where might that go? And we're like, in the river. So we'd have to wait. And I kind of share this story with you because I think from a remote sensing point of view, there's really an exciting future where we have a lot more sensors and instruments and data sets coming about. But I think one of the really novel parts of what's going to happen is when we think about relating these awesome new data sets to people's actual lived experiences, that we'll do a way better job at integrating this type of incredible Earth observations information at a much quicker pace for decision making. So I kind of wanted to kick this off by sharing an image actually that my intern, her name is Chanel McFarland, that she shared with me of the Upper Klamath Lake, let's see, right there. And here she is. So this is Chanel McFarland. She's from Northwest Indian College, Squaxin, it's Scohomish in Washington. And she shared with me about these, wrong one. These endemic fish species. They're really cute, these suckerfish, and they lived in this lake. And that this is a neighboring tribe to hers, and she wanted to study Upper Klamath Lake because there's an EMIT image. So that's, EMIT is the Earth Mineral Dust Source Investigation spectrometer that's on the International Space Station. In my new role, I was recently appointed to be the aquatic applications lead for it. So we've been working on trying to see aquatic applications of this new instrument on the ISS. So we were just like, all right, let's take a look at what you're seeing. And I think over the time she was starting to teach me about like this is one of the largest lakes in Oregon. It has HABs every year. It has changed the way people interact with that lake. So what she did was she, as mentioned, looked at the cyan imagery that's from Sentinel-3 Oceanland Color Imager, which is at 300 meters, and started to compare it with the EMIT imagery from the International Space Station. EMIT is at a finer spatial resolution. 300 meters for Sentinel-3 Ulchi versus EMIT, which is at 60 meters. I know 300 meters versus 60 meters is not really a good matchup comparison, but a 60 meters width is about roughly the width of a soccer pitch or football pitch. So when we started to look at this imagery, you see much finer spatial patterns, which really started to push you to think, why are we seeing that there? Are there certain places around the lake that is actually more conducive to creating certain patches within the lake? So Chanel has since gone on to, now she does astrobiology research, applying imaging spectrometers to other planets. But she kind of started to help me repackage how do we think about remote sensing of non-point source pollution. And I kind of made a cute 3 C's of different ways we think about it. It's mainly a memory tool for me to kind of encapsulate all of the remote sensing research that's done at JPL and at this axis. So I kind of think about it. We can look at things like surface cover. So this is an EMIT image over North Africa, and one of their key objectives was to map key minerals that, if lofted into the atmosphere, have essentially cooling or warming impacts essentially on our planet. You can also take that to further not only map minerals, but vegetation, aquatic ecosystems like Chanel, but as well as starting to look at the composition of shallow benthic ecosystems from a more of a catalyst perspective. What are those big mechanisms that move whether it's nutrients or surface cover, and changes it in a way that ends up in water bodies. We have a lot of people that work at the wildfire front as well as floods. Not exactly an expert on the floods, but I'm happy to connect you with people in our group that work on the SWOT instrument, which are looking at that. And then lastly, we're looking at consequences and Lake Erie Modus Aqua image. And this is where we can start to see, all right, when we have our surface cover, we have a sense of adjacent things going on. We can study maybe these catalyst events that change that cover or change what might be input into a watershed or systems. And then we get to this, all right, what type of algal bloom might it be? Or is there a situation where we might need to really think about our public health advisories? So I'm going to touch upon these really quick. So I also have a different hat. I don't really wear a lot of hats, so I've been thinking about changing it to like shoes. Like I wear a lot of different shoes because I have a lot of shoes. But I sit as a NASA Surface Biology Geology Mission's aquatic coordinator for the Visible to Shortwave Infrared Instrument. That's a mission that's going to be launched later in the decade that's going to be mapping land cover composition. And right now we're actively developing algorithms that can start to look at shallow ecosystems, piece together get information on bathymetry, the water column, optical properties, how that might relate to biogeochemical properties, as well as benthic fractional cover. And the suite of those things together give us a much better understanding of those conditions there. And selfishly, I obviously am starting with the Kaneohe Bay image. Also, there's really burgeoning work that's led by Michelle Gurak, principal scientist, and actually starting to look at potential plastic sources, not only with the MIT, but with airborne imagery, specifically Avarice Next Generation. And this is a map created by Phil Broderick, also at JPL. And he's applied a plastics matched filter approach over this area in India and started, when you see those like blue speckles and yellow dots, you're looking at really specific features in the shortwave infrared. And if there's like an absorption feature there, that might be indicative of a plastic source. So we're just starting up a lot of this work now. On the catalyst front, this is led by Mandy Lopez these days, and she's looking at coastal watershed linkages between land and sea in relation to wildfires. And when you're combining that remote sensing and modeling information, you can get more information about what is the discharge rate, sediment loads, bacterial information. Feel free to contact her, but I'm also more than happy to make connections. She's working a lot for Woolsey fire impacts. Lastly, Christine Lee. She's a group supervisor of water and ecosystems and do a lot of partnering with UC Merced's Erin Hester. And this is a recent paper that her graduate student, Brittany Lopez Barreto, published in San Reservoir, and she looked at Sentinel imagery, so Sentinel 2 and 3. So those are both multispectral sensors from the European Space Agency, and they're getting a chlorophyll algorithm and applying it across the reservoir, and then comparing that with toxin information here. And one of the big things is that when you start to piece together all of these Earth observations, you can start to contextualize in scenarios where you might not have somebody out on a boat taking a water sample. So I just wanted to do a brief highlight on all of the great work being conducted in our group. And I'm kind of going to transition now into really some of the key challenges that are coming up, and really in relation to a lot that has been coming up in this workshop. So a lot of my training has been actually on the East Coast, working with citizen scientists, water quality groups. And I don't know how many of you have spent time on the East Coast. It's pretty cloudy. It's cold, so to go and get a sample in the middle of February is not fun. There aren't a lot of volunteers. So I started to do a lot of that work, and a lot of the big questions come up is, well, we can work with individual sensors and satellites, but how do we synthesize them to actually fill in gaps in information? And this is a really nice visualization made by the Goddard's Scientific Visualization Studio that's showing that there's really a rich history of heritage and operational ocean color sensors, or these sensors that can look at making maps like chlorophyll and relating them to things like cyanohabs, and how we go about knitting together from the 1970s to present, I mean, that's really an open question and thing we really need to start thinking about. But also I think one of the most exciting things about my career at this stage is that those yellow sensors, those are new types of imaging spectrometers. So in the past we focused a lot on multispectral ones, and now we're going into imaging spectroscopy or hyperspectral sensors. So I'm gonna give you a visual, is that, so visible light wavelength range, the ones we can see with our eye, rainbow, since early 2002 for global current missions, these are really snapshots across the visible light wavelength spectrum. And they're positioned and designed to coincide with specific water quality features that would pop up that can then indicate that can be useful for a water quality map. However, we're going into new instrument designs that actually have way more finer spectral information. And one of the ways that I've heard the PACE satellite that actually just launched in February, their first light imagery just came out yesterday. I should have thrown that in here. One of the ways they kind of explained this is, imagine for the past 20 years, we've been drawing the color of the ocean with a box of 8 crayons. And now, as of yesterday, I've given you 100 crayons to color the surfaces, like ocean color, or the water surfaces. How is that gonna change the way we look at water quality? How's it gonna change the process in which we do it? And that one. And this is really a visual. So if you were to look at VIIRS, you would have, 5 different points along the visible wavelength range. It's very difficult to determine which one might be a harmful algal bloom, what might not be. But when you have more of that spectral information, you can then start to more concretely relate whether it might be more similar to a HAB species that somebody experiences versus a background diatom spectral feature. So this is actually from Indian Ocean Noctiluca blooms versus that background diatom. In addition to that, we're moving into the space where more of these are being built across space and time, and we're gonna have these incredible spectral information that not only are we starting to look at really specific features like phycocyanin, pigments, community composition, but that will be also in relation to CDOMs, descended solids. And in many ways, I think there's so much promise in all of this information. But wow, there's gonna be really so much that we really need to winnow down and filter to make it reasonable and accessible to people. So some of the work I did early in my postdoc was just focusing on 2 sensors over Corona brevis blooms, so red tides, and along central Florida. And then you can see the red tide. It shows up in ocean color imagery, but also you can see it there. And I think one of the most surprising things for me was that there are these weekly maps that have been generated since, I guess, late 2000s. And you see that you can see the cell count along the coast, and that background map is actually modus aqua, or an image of fluorescence. And I was just like, I found this on Facebook. Like, this is on US News. This is, the public is exposed to some of these types of measurements. And it's just like, why not? I think when we were talking, the earlier panel, it's just like, let's lean into how do you make measurements or instrument design that's complementary to this type of information. And one of the really cool things of working with Christian Frankenberg here at Caltech was he was starting to put out these papers related to Sentinel-5 precursors tropomi instrument, tropospheric monitoring instrument. And actually this instrument can detect fluorescence in variable atmospheric conditions. So what we did was, we're like, well, maybe we can fill in some of these gaps on a weekly basis. So we wanted to check first if they were consistent. And actually there's a really big bloom in the 2017 through 2018 time window. And we found there's like, wow, so during these really big blooms, we have these 2 sensors that are complementary, they are agreeing with each other. And then we wanted to look at, all right, let's look at a week where they said there's this enormous bloom that happens in the weekly composite. And then when we pulled the map, we realized for the modus aqua, or this imaging spectrometer that can really only detect in like atmospherically clear conditions, we only really had 1 image from that like really big week. But when we start to find these complementary sensors, we can start to see how they can fill in gaps for one another. So this is some work that we're trying to continue to grow now, not only tying in things like Modus Aqua and Tropomi, but other currently operational sensors like Sentinel-3, Sentinel-2, et cetera. And timing-wise, I might have to run through some of this, and that's fine. To kind of go back to emit at those finer spatial scales, one of the questions when we were working on this project with Chanel was also can something in a finer spatial resolution inform downscaling these larger pixel sizes? I mean, and this was just timing worked out. So we're just starting to dive into this now. And what we're finding is that if you were to take a 60 meter pixel and then you would take a bigger, or you double, or take a 3x3 meter or 3x3 box, average it, and kind of keep going up, you would find that a lot of the there you are. We utilize a lot of the spectral information in the 620, 650 region. So we see as we get bigger, spectral information or spatial information, these properties are actually relatively consistent. It's actually once you get to the farther end of the spectrum where you have actually more sediment interactions and all of that. So another really open question we're working on, as well as optical and thermal properties. On the International Space Station, there's also ecostress, which is a thermal infrared radiometer. So now we can start to look at what is that relationship between cyanobacteria, I say expression, at least, I don't know, I think sometimes at these snapshots, you're like, what part of the life cycle are you in? Like, we still need to really dial in on understanding their expression at the moment a sensor goes over them. But when you can start to pair that with something that's mechanistic, like a thermal property, you can start to piece together, are you seeing more HABs in warmer waters? What does that mean for increased stratification in these waters that might have experienced incredible warming in advance? So I think to kind of take us to the end, just a general recap with remote sensing instrumentation. If it's helpful for you, I think about it in a cover, catalyst, and consequence sense. We can start to look at really the surface color or cover. Really, what are these agricultural fields? Compose them from imaging spectroscopy. Starting to look at remote sensing during catalyst events where that might move surface composition into waterways, and then potential consequences like what you're seeing in this HAB here in Upper Klamath. And given the big challenge of lots of new and exciting novel instrumentation, I think really one of the most exciting parts of my career is thinking about how do we co-produce new data sets and products that get us quicker to decisions. And yeah, I guess very happy to be here and collaborate with folks that are interested. Thank you.